Artificial Intelligence Doctor. User question. How to build an agentic endocrinologist. GPT-01 answer. Building an agentic endocrinologist, i.e., an AI system or digital assistant specialized in endocrinology, requires combining medical domain knowledge, robust data handling, and safe, explainable AI practices. Below is a high-level roadmap that outlines the key steps and considerations involved in creating such an AI agent. Note that no AI system should replace a qualified medical professional. Rather, it should serve as a tool to support or augment clinical workflows. 1. Define scope and use cases. Narrow down tasks. Determine exactly what your AI endocrinologist should do. For example, provide general endocrinology education to patients. Assist clinicians in differential diagnosis for thyroid disorders. Offer treatment suggestions or best practice guidelines. Summarize and interpret lab results, e.g., hormone panels. Identify user base. Is this AI for clinicians who already have significant expertise and need quick references? Is it for medical students who want interactive study support? Is it for patients seeking simple explanations of lab results or medication guidance? Establish boundaries. Decide how far the system will go, e.g., purely educational, decision support, or partial automation of workflows. Include disclaimers to remind users that the AI is not a substitute for real clinical judgment. 2. Acquire and curate data. Medical guidelines and literature. Gather up-to-date clinical guidelines and consensus statements, e.g., from the American Thyroid Association, Endocrine Society, ADA for Diabetes Management, etc. Include reputable textbooks, peer-reviewed articles, and continuing medical education resources to ground the system in authoritative knowledge. Structured datasets. Optional if the system interprets labs or patient data. Utilize de-identified clinical datasets such as Mimic4 if available under the right licenses, or institution-specific EHR data, ensuring compliance with data privacy regulations like HIPAA or GDPR. Curate endocrine-specific lab values and patient outcomes, e.g., TSH, T3, T4 levels, HbA1c values, etc. Quality control. Partner with medical experts to annotate or verify the dataset. Filter out incomplete or inconsistent data. Use domain expertise to craft a gold standard reference set for model evaluation. 3. Select a modeling approach. Large language model, LLM, plus domain adaptation. Start with a pre-trained general LLM, e.g., GPT-like models, BERT-based architectures, which already has strong language understanding. Fine-tune or prompt-tune on endocrinology-specific corpora, guidelines, articles, curated QA pairs. Use domain adaptation strategies such as low-rank adaptation, LoRa, or instruction tuning for medical tasks. Rule-based plus knowledge graph, optional hybrid approach. For critical decision pathways, incorporate rule-based logic or knowledge graphs derived from clinical guidelines. Integrate these rules with an LLM that can handle unstructured queries and provide explanations. Reinforcement learning from human feedback, RLHF. If your system is conversational, RLHF can help align answers with best practices and the style of medical communication. Have medical professionals act as annotators to provide feedback on correctness and clarity. 4. Incorporate clinical reasoning and safety features. Chain of thought prompting / explainability. Encourage the model to think aloud, internally or as hidden chain of thought, to ensure it methodically arrives at a conclusion. Provide short, clinically relevant explanations in the final answer, e.g., referencing guidelines, explaining hormone feedback loops. Confidence estimation. Implement a mechanism for the AI to indicate when it is uncertain or to provide references for its recommendations. If the confidence is below a certain threshold, the system should advise the user to consult a specialist or to recheck data. Medical safety constraints and guardrails. Hard-code certain safety checks for emergent or life-threatening situations, e.g., suspected diabetic ketoacidosis, thyroid storm. The AI should instruct the user to seek immediate medical care if certain red flag symptoms or lab values are reported. Ethical and regulatory considerations. Comply with relevant medical device regulations if the tool is intended for clinical use. In some regions, an AI giving diagnostic or therapeutic advice might qualify as a medical device, requiring additional testing and approval. Maintain user privacy by following HIPAA, GDPR, or other data protection laws. 5. Implement an agentic framework. Agentic task handling. Rather than merely answering queries, design your AI to proactively suggest next steps. For example, if a user mentions hypothyroidism symptoms, the AI might suggest checking TSH levels, referencing standard guidelines for diagnosis, or recommending further reading or a referral. Integrate an action loop so the AI can refine follow-up questions based on user responses, e.g., have you had your TSH levels tested within the last 6 months? Context management. Use conversation state tracking to keep a running log of the user's previous questions, symptoms, or lab results. Ensure the agent can recall relevant information across multiple turns to provide continuity and deeper insight. Integration with external tools, optional. Connect the agent to external systems, e.g., EHR, lab reporting, under strict access controls so it can pull in new lab results or medication lists for more accurate, context-aware advice. Implement role-based access control and encryption to protect sensitive data. 6. Testing and validation. Clinical expert evaluation. Set up structured tests where endocrinologists or clinical staff evaluate the AI's answers against real cases or recognized guidelines. Have them rate the relevance, accuracy, and clarity of responses. User testing. Run pilot tests with the targeted user population, patients, medical students, or clinicians. Gather feedback on usability, trustworthiness, and user experience. Quantitative benchmarks. Evaluate the model against standard medical QA benchmarks or domain-specific tests, such as classification tasks, e.g., identifying hyperthyroidism versus hypothyroidism based on lab data. Track metrics like accuracy, F1 score, or custom domain-specific metrics. 7. Deployment and monitoring. Pilot launch/beta testing. Roll out the system to a limited set of users. Monitor interactions to identify recurring errors or misconceptions. Ongoing model updates. Regularly retrain or update the system with new guidelines, new research findings, or expansions to cover more endocrine disorders, e.g., growth hormone disorders, adrenal insufficiency, etc. Monitoring for safety and drift. Continuously evaluate the quality of responses to ensure no drift toward outdated or unsafe advice. Establish a feedback channel for users to report incorrect or concerning outputs. Governance and compliance. Maintain a documentation trail for updates and data lineage. Periodically review compliance with medical safety standards and data protection regulations. 8. A note on ethical and professional responsibilities. While the technology can be impressive, it is essential to emphasize: no AI replaces the judgment of a qualified endocrinologist. Real-world patient scenarios are complex, and subtle context can dramatically change management. Human oversight is key.